then hopefully have Natasha come in for that. So Denis is going to be speaking on new clues in the nature of Hercules X1 35-day cycle. And as a reminder for your speaker that you'll have 12 minutes followed by a warning, a 3-minute warning, and then 3 minutes of questions.
Right. Okay. This is something that we're talking about the past year roughly, looking at a whole set of archival data from RIT and also Leahy satellite on Hercules X1. The PhD student has been working on the theoretical modeling and on the DEP data analysis. So that is to study the 35-day cycle for Hercules X1 and just determine its properties. So at the ASM we have 14 years of data. The idea was to measure the cycle lengths and turn-on times. I'll say a little bit more on that later. In RXT PCA, we have much higher sensitivity, but the data coverage is not continuous like it is at the ASM. So ASM is 14 years continuous roughly, and the PCA is about 53 days of integration time over the 14 years. Okay. So Hercules X1 is a really old system. You wonder why we're still studying it because it's so well known. There's nothing new to learn. Okay, so we know that it's the standard X-ray pulsar, and the orbit is very well measured. The 35-day cycle, though, is not so well understood as dips, which are not understood. There's lots of different proposals for what's causing that. Here's the summary of what the 35-day cycle looks like. So here's goes from 0 to 35 days. This repeats. It's not strictly periodic, but a few years ago with Matt Scott put together, using the first couple of years of RXT data, the light curve by using BATSI to line up the turn-ons and overlay the 35-day light curves. So you see a bright part, which is the main high state, and then two low states, and then a short high state in between. On here we've marked, it's been aligned so the eclipses, the 1.7 day eclipses line up exactly so we can see eclipses, and you also see dips, which are the drops which don't line up with the eclipses. And so we know that many years of work that this whole cycle of main high and short high is caused by the accretion disk, which blocks the X-rays from the neutron star reaching the observer. So here's the accretion disk model. It's a twisted and tilted accretion disk. So the outer edges are off the orbital plane by about 20 degrees. There are various papers, some proposals for the accretion disk, and this is one which gave which turned out to be the correct mechanism, which is radiation-driven warping. And here are just the geometrical parameters. Okay, so if you imagine yourself sitting in a neutron star looking out at a celestial sphere, you can map the accretion disk onto the celestial sphere, and that's what I showed here, on two cycles. So this goes from 0 degrees longitude to 720 degrees. This is twice around the celestial sphere, and the vertical scale is much stretched. It's only plus or minus 25 degrees. So you're sitting on a neutron star looking out at the celestial sphere. The observer is 5 degrees above the equatorial plane, so I've drawn a line here at 5 degrees. So if you're on a neutron star looking at the observer, over 2 35-day cycles, the disk rotates around twice, and the observer remains fixed. That means that the disk reference frame, the observer goes around twice 720 degrees as through 2 35-day cycles. You can see that the main high states correspond to when you have clear visibility of the observer from the neutron star. Short high, there's just a brief period of visibility, and again, a clear time. And the reason that it's not flat is because there's an accretion disk atmosphere, and also the inner edge of the disk is ionized, so the X-rays get in. This is the outer edge. The outer edge of the disk comes in here, that's the inner edge. Inner edge, so the inner edge allows X-rays to go through. This model has been verified. Well, actually, it was first measured back in the optical because in addition to the shadow cast on the sky by the disk, there's a shadow cast on the companion star. But instead of the companion star moving across this 360 degrees in 35 days, the companion star moves across in the deep period between the 35 days and the orbital period 1.7 days, which is 1.62 days. Okay, so here I've got a 3D model of the disk, which in order to properly model a light curve, you need to have, I don't know if I can get thermos here. You have to have a thickening of the inner edge. Whoops, okay, I won't over that again. Shorter time, but you have to have a thickening of the inner edge, and it turns out that a lot of you get Compton reflection off the inner edge, which actually gives a big contribution to the light curve. That's the dashed line, and the actual clear open view of the neutron star at the center is this lower solid line. So it's only a very small port during short high state, and then the total is the solid line, which is the data points. Okay. So on to the observations over many years. This is 14 years of the All-Sky Monitor data, daily average points. You see, the cycles go up and down, but it's hard to see it on this scale, as well as you have 2 periods when the source was shut off called anomalous low states, which I won't talk about today. Okay, so you can use this. There's 147 cycles, and the ASM isn't always on because there's various things, the satellite outages. So we have 97 well-sampled cycles, 29 with gaps, and 21 during the anomalous low states. And this just shows not the data itself, but the cross-correlation of the template with the data, so you can well detect the cycles. One result came out of this is you can measure all the cycle lengths, the well-measured cycles, and for the ones that aren't well-measured, you can interpolate. You can ignore those points, but the well-measured cycle lengths give you a nice correlation between the cycle length and the flux. And that's actually expected in this radiation-driven disk working mod. So there's a correlation there. For a long time, we've had this idea that the turn-ons occur only at 0.2 and 0.7 orbital phase, that both these have large errors, and I tested that in this data. There's the orbital phase of turn-on, and I get nothing. So it may be that this is just artificially that if anybody observes a turn-on between the end of eclipse at about 0.07 and 0.5, they call it 0.2 turn-on, and if it is between 0.5 and 0.9, they call it 0.7. And there actually is no 0.2 and 0.7 turn-ons. The previous data is not great on this. Okay, so let's go on to the other half of the analysis, and only got a few minutes to talk about our model. So we have, here's 14 years of PCA observations, so there's bits and pieces throughout the 14 years. Here's one piece of several days from main high state over here, and here's a short high state down here. A lot of them are just little bits and pieces, all from different individual observing proposals for different purposes. Notice that. Oh. Okay. So if we follow the whole thing at the well-known, using well-known orbital ephemeris, you get the nice sharp eclipses, and of course I plotted the error bars here to show that when the flux goes to really low, the error bars shoot up, but everything's okay. And now you can't really put together in one overall cycle until we've used the ASM analysis. So the motivation for the ASM analysis is to be able to phase up all of the 14 years of data, and if you do that, you get a nice main high state and a short high state. And it turns out not a single time over the 14 years did anybody observe in this part of the low state. There's a few observations here. So unfortunately, we're still missing data in this step. Okay. All right. Now, I want to say a bit about absorption dips. So absorption dips, there's been many different papers over the years, but it's basically there's partial covering with cold matter absorption. These are some data spectra showing that. Here's a sample of the of one dip in the current PCA data. So typically the count rate drops and it may recover either a few minutes or a few hours later. And the idea is to find out what is the how these dips behave as a function of 35-day phase and orbital phase. So here's plot of the softness ratio. So whenever a dip happens, the spectrum becomes harder. So basically, the spectra's softness ratio drops. This is all in dips, and this is normal. Short high state actually is much more scattered in the normal case. That's because you're looking through the inner edge of the accretion disk. There's basically two types of short high data which don't seem to be distinguished by 35-day phase, but both go into dips. And this is some low state data. So you can see, for example, here's the high state. If you put in a color count rate diagram, this is the high state, and in the dips it just drops off. And when you get to really low count rate, the direct radiation is basically completely absorbed. You just see the scattered radiation, so the softness ratio goes up again because you get more scattered softness ratio. There's just another word on here. All right, and here's the out of dip data in two energy bands, and the dip data is separated. This is now the all of the main high data plotted as a function of orbital phase. So we see that the maximum column density in the dips, the fifth spectrum, is a strong function of orbital phase, but it doesn't depend on 35-day phase. So this is contrary to most of the models for dips, and so that needs to be revised. We're currently working on that. So the dips are really, their spectral nature depends on the orbital phase and on the 35-day phase. So I'll just spend a minute or two talking about our modeling and then go on. So there's different ideas for the dips. One of the ideas which has been around for many years is first discussed in detail by 1996 by Susan Chandel. The idea is you have the normal star over here, and you have some accretion stream which goes in the absence of the disk, the neutron star will come back out, and the disk gets in the way, so you have an impact point, and the impact point will always be where the stream intersects the disk in the equatorial plane, which is basically the line of nodes of the disk. So the various possible locations of the impact point fall on the line of nodes, and you can just calculate that using geometry for any 35-day phase and orbital phase. And you can trace this impact where it moves around as a function of time, and you also know the observer's position, so you can calculate the distance between the line of sight to the neutron star and the impact point on the disk. And that's what this plot is for one particular set of parameters. So this, as a function of time, this is in days, 0 to, I can't even read that axis. So the one plot we had went to 70 days, which is 2 seconds. I think that's this one. But you get all of these changes in distance. So this is not directly a DIPS model yet, because you have to have a model for how big the impact point is and whether there's any splash. So that's what we're working on now. We don't have definite results to report, but the idea is to produce the dip timings and the lengths of the dips using this kind of model. Okay, so it's just work in progress. There's a couple of other models which are in the literature, but certainly don't work because they don't produce the right dip properties. So hopefully this work will be done by the end of the year. Here's just another one where we have a disk with a wavy edge. But there's dips throughout the whole 35-day cycle, and some of the wavy edge that people only predict dips during in a short high and not during the mean high, except in the very first cycle. Okay, so this is a little bit now, maybe just a minute or two on the UV. This is an old observation, it's never been looked at. So normal extreme ultraviolet emission from RX1 is quite modulated and can be well fit by just calculating the shadow of the disk on the companion star, taking the reflected light off the companion plus adding a disk component. works very well, but in the ALS anomalous low state, you basically don't see any X-rays directly from this neutron star, but you do see reflected X-rays off the companion. And one way to do that is to just take the normal disk model and put a little more twist into it, and then the observer doesn't see any of the illuminated inner parts of the disk because the outer part of the disk hides it from view. If you do that, you could also reproduce the reduction in the amplitude of the EUV. So here the EUV drops by about a factor of 5, and the modulation drops below detectability. So everything is consistent with just putting an increased twist in the disk.
What's the mass of the companion, the donor star?
2.3 solar masses, and the correct one is about 1.4. So this is just more of the, there is an RxCT, the observation of the anomalous low state. You see this modulation, which is consistent with X-rays coming from reflection from the companion. And this is just comparison over a couple of years showing that because the disk is recessing, you expect the peaks to move around, and in fact they do. So there's a whole bunch of different peaks, and if you overlay them, it doesn't look very coherent. Recording. So I'll just put on my summary here, and we're this model. We're currently working on. There's a lot of parameters in this stream, and we haven't actually fit the dip durations and the timing. Thank you.